Let's jump right into it. Welcome to today's Explainer, where we are stripping away the complexity to help you master an absolutely crucial, yet surprisingly easy to overlook concept in plant mechanical engineering. We are talking about nominal thickness. Let's kick things off with a practical dilemma. Say you've run all your math, and your calculations tell you that you need exactly a 10 mm plate for your design. Can you just go out, order it, and get it right away? Well, you'd think so, right? Which brings us to section 1. What is calculated thickness? When you're designing a vessel, you, as the engineer, come up with a calculated thickness. Let's stick with that 10 mm example. That number isn't just a random guess. It carefully factors in the design pressure your equipment needs to withstand, plus an allowance for future corrosion. In a perfect, textbook world, 10 mm is the precise number we'd use, no questions asked. But we don't live in a textbook. Section 2. Real-world hurdles, market and schedule. Engineering doesn't happen in a vacuum. Notice the really stark contrast here. On one side, you have the pristine, perfect math of your 10 mm calculated thickness, and on the other, the totally chaotic reality of market availability and strict project schedules. I mean, ask yourself this. What happens to your flawless engineering plan if a 10 mm plate simply does not exist in the market when you need it? It happens way more often than you'd think. When time is literally money, you can't just pause the whole project delivery schedule to wait for a custom steel order. So an engineer, or the vendor, is frequently forced to pivot and select a thicker plate that's actually available on the spot. Time is of the essence. But time isn't the only pressure. Let's look at Section 3. Vendor inventory and cost savings. Often, an equipment vendor will just take a look around their own warehouse, and what do you know? They find a thicker plate just sitting there, gathering dust in their inventory. Instead of going through the hassle of placing a brand new order and waiting weeks or months, the vendor is just going to use that existing thicker plate. Why? Because it significantly reduces purchasing costs. It's a huge win-win for the budget and the timeline. So the big takeaway here is that market constraints messing with your schedule, combined with the vendor wanting to use their own inventory to save cash, will almost always force us to abandon that mathematically perfect 10 mm calculated thickness. We just have to adapt. And that leads us perfectly into Section 4, defining nominal thickness. This brilliantly resolves our whole theory versus reality conflict. Nominal thickness, which, by the way, is totally interchangeable with the term ordered thickness, is quite simply the real-world thickness of the plate that actually gets bought and used to build the equipment. Not the theory, the reality. To put it simply, calculated thickness is our theoretical target, the one born from our formulas. But nominal thickness, that's our practical, boots-on-the-ground application. It's what is actually being welded in the shop. So how do we actually use this? Section 5, the corroded thickness formula. Here is how this plugs into the critical math you'll be doing every single day. If you want to know how much steel you'll actually have left after years of harsh plant operation, you start with your real-world nominal thickness. Then you subtract the corrosion allowance you expect over time. And boom! That gives you your final corroded thickness. It's a simple step, but it's absolutely crucial. So, as you step into your role, I want to leave you with this final provocative thought. If one completely mundane variable, like what happens to be sitting in a vendor's inventory, changes your plate thickness, how does that extra weight, that extra strength ripple out to affect the foundations, the piping, the entire plant design? It's like a giant puzzle, and everything is connected. Keep that in mind as you dive deeper into engineering.